In this video I want to take a look at some images to establish another falsehood perpetuated by flat earthers concerning what refraction is capable of. It won't be a technical video in any way, no equations, no curve calculators, it won't even be discussing the shape of the earth. We've all heard the contradictory claims that flat earthers like to make when it comes to observations and the atmospheric effects that come into play. We've seen them deny refraction altogether when it's in their best interest to claim an observation proves flat earth, like Toronto and Chicago skylines, Taboo conspiracies, mirror and torch observations, Nathan Oakley's constant cry of we can see it because it's there, the more recent Monterey Bay mirror observation, and so on. And in the same breath, they'll invoke refraction using made-up terms to explain the angular size of the sun, the local horizon, and soundless images of the Lake Pontchartrain causeway, etc. By taking a look at some real-world examples, starting with some of my own, I'm going to show that refraction is more than capable of causing the path of light to deviate by very large amounts, and that undermines most so-called flat earth proofs. So to start off with, we're going to be looking at the island of Ailsa Craig. If we look at this image for a second, this is just a reference image so we know what the actual shape of the island is. This is a high elevation profile shot, so it shows us the actual shape of the island and how it should look before we then move on to look at the examples I'm going to give you. Now I've shown before that at low elevation not all of the island is actually visible, some of it is chopped off. So we can still see, if we ignore that bottom part, that it's a gentle slope on the left and a slightly more severe slope on the right, which then becomes steadily more severe over two sections here. So this is the kind of general shape we're expecting to see on the island, and we'll use that as a reference for this selection of images I'm going to show you. Right, so now we're going to look at examples of where refraction is affecting the shape of the island. Starting off with a relatively mild example. You can see over here this peak that appears to be jutting out on the side of the island, which is something that isn't there on the normal profile of the island. So this is an effect being created by refraction. Now this is only a mild example, as I've said, and yet if you consider the overall size of the thing that you're looking at, we know that this must be many meters worth of a deviation from the norm. So if you think about, for example, if someone was standing on this island with a mirror, this area here being projected out to the side would actually cover a much bigger area than the person in the mirror would take up. So even this small little peak already tells you that it's possible to have light deviated by the atmosphere to a degree which is high enough to account for certain observations and to rule out claims like saying if you see something it must be there, because that peak isn't there. You're seeing it because the light from the island is being modified in some way by the atmosphere so that it comes to your eye by a different path. But this, as I say, is only a mild example, so let's look at some better examples. This is going to be harder to see because there was a lot of haze on the day that this happened, but hopefully you will be able to make out the general shape that we're looking for here. So this is the top of the island and the start of the slope and the slope here, but you can see once we get to this kind of level here, the entire lower portion of the island is being completely misshapen by the effects of the atmosphere, bending the light through it. So now it looks like it's squared off completely on both sides. Now the island is over 1100 feet in height, so if you consider the overall area that you're looking at here, then it's easy to see that the light from the island is being deviated in such a way that it's creating the illusion of several hundred feet of land being displaced both horizontally and vertically. Now this kept shifting around due to the atmosphere, so the shape kept changing. So if again, this might be hard to see, but I'll trace it with the mouse. So you see now, instead of being squared off, there's more peaks coming out, it's more jagged and misshapen. There seems to be a sharper corner over this side, and then it can dips in and then back out again. So it's constantly changing its shape, and all of this is the result of refraction. So I'll just play a little section of video that I took at the time. It's not the greatest, but it just shows where the island is in relation to the camera and the fact that it was actually happening live and it's not some Photoshop image that I've created after the fact. But you can look at it, if you look at it, you can see the shifts in the shape, the peaks extending out way to the left there and so on. It is completely misshapen, nothing like the original island at all. So it started off looking sloped, then squared, then it looks like it's got a saucepan lid on top of it. I mean, it's constant changes, and as I say, each of these areas that you're seeing that are extending out beyond the edge of the island, this is hundreds and hundreds of feet worth of projected light. So panning to the right of Ailsa Craig from that location, we have the tail end of the island of Arran, and this photograph here is again a comparison photograph, so we can see the shape that that piece of land would normally take. Now, if you go into Google Earth and get an elevation profile for this area, the section of land you're looking at averages from between around 200 feet up to 600 feet, and then heading up this way, almost 900 feet. So in general, this area here towards the end is covering a range between 200 and 600 feet. So the same thing's affecting the island here, and if you watch it, it's almost like clouds forming sometimes. Now, pause it for a second. I've just shown you the way the island is normally shaped, and as I've said, the lowest part you're looking at here is about 200 feet, climbing up to 400 and 600. So in effect, what appears to be happening is you have this big massive chunk of land which is several hundred feet in height being projected up into the air by several hundred feet, and that's just the lower area of the island. So again, if you consider these examples, especially things like mirrors that are a couple of feet long, that are, according to the curve calculators, say anywhere between 10 and 40 feet behind the curvature, being able to see the light from them is nothing. It's very easy. The atmosphere is more than capable of doing much stranger things. It's handy to have this boat, the fishing boat in the front, for a frame of reference. Now, we already know, as I've stated, the general elevation profile of the island, but this is another way of gauging just how much this is being affected. Now again, we're not looking at any specific figures here, we're just using estimations, but the boat itself must be several metres in height. If we take, say, the height of a few people as a guide, so 3 to 4 people, and average it out to 6 foot a person, just as a rough guide for the height of the boat. So let's say the boat is some 20 odd to 30 feet high. Even as a rough guide from the boat, knowing that it's maybe around 30 feet and allowing for how much smaller it would look if it was further away like the island was, we can estimate that this is several hundred feet worth of refracted light, making it appear as though the island is twice the height that it actually is. And just as we watch this play, just imagine a line running across here somewhere representing the horizon on a curved earth, and then consider what you would see up above that horizon, all of this. Now, how would Nathan Oakley's claim of "we see it because it's there" explain that? It simply wouldn't. So it's an inaccurate claim to make, to say just because you can see something it must physically be there. We know the atmosphere can deviate light, and when you see something, all you're seeing is light which is being directed into your eye. So if it takes a different path and then makes its way into your eye, you're going to see something different. So now we're looking the other way, and this is the Ayrshire coastline. Now I actually missed some of the most extreme examples that happened here because I was looking at it and kind of admiring it, if you like, and then I decided to move around and try and capture it with the camera, by which point it changed, and this whole effect only lasted for a relatively short time before it all calmed down and went back to normal again. Now, I know it's really fuzzy and hard to see, and I know from being there personally what this looked like. You might be getting the impression that the only thing that's happening here is straightforward mirroring. But what's actually happening with some of the buildings, and it's a little bit easier to see with some parts than it is with others, especially for me because I know from seeing it when I was there, is that actually the mirroring is happening more than once. So the images are getting projected up and flipped, and then projected up and flipped again. So for example, this building here has a mirror image of itself up above it, but then there's a more compressed version which is up above again. It's the same with this stuff, it's just some of it is harder to make out than others. This building here, same again, you can see that it's got a mirror image of itself above it, but it's flipped over. And then it's been projected up again. This is the same as the lower image, but it's more compressed. So this was happening along the length of the coastline, and I don't necessarily have the best examples on camera. So I'll show some more in a minute and we'll maybe get some better examples, but the point I want to make here is that you have a building which is several metres in height, and then several metres above that, an image of that building is being projected up here. So again, if we consider this just as being, for example, a mirror and just the source of light from here, then it's easy to see that that light can just as easily be projected several metres up into the air. But on top of that, it's then being projected even further up and being flipped again. So we could easily have either blockage up to here or blockage all the way up to here, which if you consider the general height of what these buildings, these are like warehouses and stuff. So let's just say the average height is somewhere between 30 to 40 feet for the buildings. Again, you're looking at, say, in the region of 100 feet, maybe more, up into the air of potential deviation of light due to refraction. So this is the point that we need to understand, is that the atmosphere is more than capable of making these kind of changes to the path of light, and that flat earthers who think that these things aren't possible are just wrong and they're fooling themselves. The distance to the first point here is roughly about 10 miles, and then the further you go along the coast it's getting further away. This area is maybe around about 12-13 miles. So it's a several mile stretch of coastline that's all being affected, and you can see the way these mirror images are occurring. Very high up in the air compared to the original source. Now this is an excellent example of why I wanted to show this specifically in relation to the claim that we can see it because it's there. If you compare the lower image of this warehouse to the image that's been projected up above and then flipped again, if this was the horizon here running all through, you would see this and you would think you were looking at the top of the building, just the same as if you were looking at this here. You wouldn't know the difference. Your eye can't tell the difference. The only reason we know this is a mirage is because there's nothing blocking between here and there. But this building's image is being projected way up above where it's actually located. So again, we can see it because it's there? No, not always the case. Refraction absolutely can lift something up by many, many feet. And the idea that something small, like a mirror, flashing a little bit of light, or a torch, just because it's physically located near to the water or down at the beach, can't be projected higher up into the air before it actually makes its way to your eye or the camera. It's just a complete falsehood. This is an excellent example because it's showing that it's not only been projected up, it's been stretched so out of shape and so on, and it makes it look as if there's a massive wall of some kind of building or whatever here, when in reality all that's there is just some building located roughly down here, and all of this simply doesn't exist. If I put it back and just let it run while I'm talking, you can notice the scintillation in the atmosphere, the turbulence, the way everything keeps waving and moving around. It's generally hazy and fuzzy. The boat's a good example here to give us an idea of what I'm talking about. If you look at the way the image of the boat appears constantly shifting due to the atmosphere, these kind of conditions are familiar. If you go out and take observations, you will find that this is the kind of hazy, distorted atmosphere that you will encounter quite a lot on days when you're going to get some miraging effects. It's not always the case. Sometimes it's cooler days and it appears clear, but you still get some of that clear, sharp mirroring effect. But these kind of conditions, these hazy, fuzzy, turbulent conditions, you're pretty much guaranteeing you're looking at images that are affected by refraction. Just taking an example from these buildings here, they're all relatively small, sitting at the coastline here, and yet look at where the refracted images are. They're much bigger, more stretched, and they're way, way up in the air. Far, far above where they're originally located. Now if you just see this, think of this as one individual blob of light, how can you possibly say that that is the location of the actual building when it's actually situated down here? The same applies to the torch, the same applies to the mirror. So just finishing off with this example, the mirage effect is changing all the time it's being filmed, and now it's a much more obvious inverted kind of mirroring effect that you're seeing. But again, consider the locations of the original buildings that you're seeing, and then look at the images and where they're being projected to up above. If you can see things like this happening in the atmosphere, then you can definitely see light from a torch or a mirror or something similar being deviated in the same way, being refracted in the same way, and therefore being able to see some little blob of light in the distance proves nothing about its original location. So before leaving this example of mine, again we've got something in the foreground that helps us provide us with some scale. You've got people standing on the rocks here, and they're much, much closer to the camera. These are about 1.5 miles away, and as I say, this is between 10 and 12 miles away. And yet, even at that scale, considering how much closer they are to the camera, it's a good gauge again to show that everything you're seeing up here is hundreds of feet up in the air. So now I want to share a piece of footage by Mathias Kp, which I asked permission to use. I'm just going to show a section of it. And what it does is it shows a similar effect looking at some buildings at the distance. This is a time-lapse of the turning torso building. And what you're looking at is these buildings here. So in this part of the time-lapse you can see where they're sitting, and I'll just let it play for a little second. Now if we look at this later part of the time-lapse, we can see that the light from the buildings is being projected up in a type of mirage, creating the illusion again that the buildings are much taller than they really are. So what this shows us is that atmospheric refraction can again take the light from some original source and appear to project it higher up into the atmosphere, so that an object appears to take up a location in space far above where it actually exists. So if we put this back a bit and look at the buildings when they appear to be mirrored and stretched and so on, and then consider that somewhere across here is an obstruction, another horizon line much higher up, then all you would see is this section of the buildings, and without fine detail especially, you would never know what you were looking at. You would believe you were looking at the actual buildings when in reality it is not the physical building itself. The building itself is much lower down. So to round this off, what I'm going to do is look at some footage which is very specifically tied to flat earth. So the first is Skunk Bay time-lapse, which has been used by a multitude of flat earthers, and as I've said, by Anthony Riley to try and disprove soundly. Now I'll just let a bit of it play so you can see generally what's happening in this footage. You can see how much the land appears to rise, how much it compresses, and so on. So at any given time, what you're visibly seeing is not only different in its shape and appearance, but also in its location in space. The fact that refraction is capable of making this much of a change in the apparent location of an object rules out any claim they want to make that because they can see something, it must physically be there, and whenever they do these tests at the beach and so on, or across lakes, that they are only seeing the torch or the mirror or the laser or whatever it may be because the body of water is flat and you're seeing directly across it. So what that means is that flat earthers have been debunking themselves by referring to footage like this anyway. You can't show something like this and then say Taboo conspiracy is definitely only showing you a torch which is down at the beach. You can't show footage like this and say D. Marble's laser was never deviated by the atmosphere. You can't show footage like this and claim that we're seeing the mirror at Monterey Bay directly. This kind of footage completely debunks it by showing you what refraction is capable of. Finally, let's take a look at Lake Pontchartrain and actually think about how some of the complaints that flat earthers make about this footage actually prevents them from making many of their own claims. So this is a time lapse that Soundly made of the causeway, and you can see the curve. Now, I have had lots of people tell me that that curve is due to the atmosphere, and one of the reasons why they claim to be able to say that there's weird things happening in the atmosphere is because we can see elements of the scene changing slightly over time. Now, there's a faster time lapse towards the end of this video. I'll put that on so you can see, and I want you to pay attention to the water tower in the background. Right, watch how much this water tower deviates. It's like it's rising and falling, rising and falling. And you can see the whole forest at the background appears to be doing the same. Now, as I said, flat earthers like to use evidence like this in this video to try and disprove this video by somehow claiming that it creates this nice, perfect geometric curve and causes things to disappear below the water. But let's put that aside for a minute and think about the implications of the refraction that's been noted by flat earthers. The same thing I've been saying with all my footage applies here. When it comes to these claims by people like Taboo, D. Marble and the guys who did Monterey Bay, the amount that this background and water tower shifts according to refraction, the very thing that flat earthers have latched onto to try and disprove soundly, disproves any of those claims, because it shows yet again that yes, the light can be deviated by refraction in the atmosphere far beyond its original location, its original physical location. It can be moved, it can be shifted up, and then when you see it, what you think you see isn't physically in that location. So to say, for example, that the Ferry and the Divine Plains footage can't have its position altered to make it appear as though it's lifted by a few feet or a few meters, that's not all that extreme. Flat earthers like to act like it's extreme because it goes against what they believe. Yet at the same time, they will say that this curve here, which is as bad if not worse, is down to atmospheric causes. So we're seeing again that flat earthers are just patently wrong when the evidence is viewed, and that they're complete hypocrites who will contradict themselves on a whim because they have to ad hoc and pick the argument that appears to suit their position whenever something goes against the claims that they want to make. So people who support flat earth not only are hypocrites, but they need to decide what it is that refraction is capable of. You can't have this option of picking and choosing when refraction is or isn't real and what it is or isn't capable of doing. Atmospheric refraction exists. Anybody can go out and witness it happening. It doesn't always result in inferior mirage, and it absolutely and unequivocally can deviate the path of light by several hundred feet. So all of your excuses and all of your claims are null and void.